long encoding, like what was vulnerable with IIS a while ago. You can also say C1A1, which is a valid overlong encoding. Well, for each of the, you can actually encode it up to a 6-byte long encoding. Well, for each of the 6 bytes that you can encode it for an overlong encoding, there's 2 bytes or 2 bits that are ignored in the actual processing of the decoding of the character. So you can make them do random junk. So example, to do an overlong invalid encoding, you can make A be C121 or C161 or C1A1 or C1E1. I'm not even going to go through the 3-byte. There's also, you can do 3-byte, 4-byte, 5-byte, and up to 6 bytes. So really, there comes out to be, for just the letter A, there's 125 ways to encode A if they're using UTF-8. What's interesting is not all the browsers handle UTF-8 correctly. Some of them handle a number of the valid overlong encodings. Some of them handle invalid overlong encodings up to a certain size. Some of the versions of IE support overlong encodings up to 3 bytes deep. Some of them support up to 6 bytes deep. So again, what the browser supports and what the IDS support, you have to handle all of those.
Now with client-side encoding, there's also a difference in terms of, this isn't really an IDS and IPS problem so much as it is a general problem with anybody trying to do malicious code detection. What you'll notice is the malware, the antivirus, the IDS, the IPS, the WebSense, all these different companies are basically trying to do the same thing these days. There's so many client-side attacks that everyone who's doing client-side attack detection is kind of going towards the same point, which is being able to decode any HTML page, have JavaScript virtual machines, all sorts of things, trying to figure out whether an attack is really an attack or not in a web page. And all these different techniques here don't only apply to the IDS, they also apply to things like your antivirus looking for an automated malware install as you browse the web. So this goes a little bit further than IPS in terms of the impact for this and the folks who really need to care about it.
Yeah, and again, this makes it great fun for cross-site scripting things. So we're going to talk about some of the different JavaScript evasions. You should all recognize the first one. Say, I want to embed the string evil into my HTML string. So there's a number of different ways that you can do that. You can add it with an onload. You can say, onload, do this JavaScript handle. So you can do if you write an IDS string that actually looks for evil, you can do something you can do what's called unescape. So take a hex string, unescape it, and make it the regular ASCII string and insert that into the HTML. You can do a number of different things that cross-site scripting type attacks. You can say, make this JavaScript happen inside of a font tag. So set up the background as a URL, which the URL evaluates to some JavaScript.
The ECMA script spec also allows unescape with the %u stuff. So when the IIS vulnerability came out, people realized that, hey, you can do encoding with %u, byte value. And like, well, why does this work? This isn't part of any HTTP spec. This isn't part of any URI spec. But it is documented in the ECMA script spec, which is what defines JavaScript and JavaScript-like languages. %u is nifty because depending on what the endianness of your platform is, it'll decode to a different thing. So for instance, on the x86 and little endian platforms, if you do %u 01, 02, that actually becomes 02, 01. But if you do it on a PowerPC system, that ends up becoming 01, 02. So depending on what system you're on, you can use unescape with the %u sequences to decode it differently and confuse whatever the IDS or anything that's parsing that HTML file.
But additionally, some of the other ways that you can do that. One of the great things about HTML interpreters, they try and, there's a lot of people out there that are writing HTML that have no idea how HTML actually works. So they do a lot of things to make it so web pages render the way that you think it's supposed to, even if it's not totally correct. So you can add spaces inside of your JavaScript. So you can say JAVASC script. So instead of actually saying JavaScript, it's all broken up with spaces. Also tabs and new lines also work there as well. Your IDS has to handle that too. One of the great things is, so the same thing that we said before about inserting the invalid characters, the FFFE, or the FEFF, which says, hey, this is UTF-16 big endian. Well, if you embed a number of browsers, if you see that at all, it just removes them. So as it's transferring across the wire, you're going to have FF or FEFF. But when the browser interprets it, it's going to say, hey, that's an invalid character, just drop it. And then, so like you said, if you embed it inside of a script tag, well, when it goes across the wire, that doesn't look like script to any normal person looking at it or an IDS looking at it. But when it's evaluated by the browser, it's going to say, hey, that's a script, and do an alert. So one of the great things is, so people are doing things like for prevention of cross-site scripting. They're evaluating and saying, remove where you see script. Well, one of the great things is, so most people are using PHP for that, or Perl or whatnot, a number of the different regular expression engines, if they are compiled to support in Unicode encoding, which most of them are not compiled by default to support that, if they are compiled to support that, the Unicode encoding is somewhat broken. So if a character set is invalid, it'll just say, it'll stop processing and just return back as okay. So you get into if you add, FF or FE inside your, into your form field that you're submitting, when it's submitted, and then the regular expression tries to remove all of the stuff, when it gets to the FF or the FE, it'll just stop processing and say, okay, the rest of the string is okay, return it, and then when it's and then the application continues to use it thinking it's safe because it passed it through its perfect regular expression. So one of the other ways that you can hide stuff in web browsers is you can encode things in base64 and include them as an object inside of an object tag. So the example that we gave here is is a base64 encoded string of evil text. One of the things that the IDS vendors are having a problem with is they don't want to implement a base64 decoder in line. Well, unfortunately, they started writing signatures for the base64 encoded stuff. The problem is, so the string foo, well, in HTML land, spaces are pretty much ignored. So foo and then foo prepended or appended with a space or new line or whatnot are encoded differently in base64. Well, unfortunately, a number of IDS vendors are implementing signatures for base64 encoded attacks. Well, add a space at the beginning of your attack, the entire encoding is now wrong.
A little bit about compression issues. There's actually a IDS recently added support for HTTP compression as part of their decoding protocol, and won't get into too much, but we did test them with what's called the zip bomb. Most people are familiar with this as being, a zip file that's a really small size. When you expand it, it becomes this multi-gigabyte file that chokes up your system. And it's a fun attack against things like SMTP gateways, things like that. This also applies to things like HTTP requests, though, and HTTP responses, because you can do gzip encoded responses for all HTTP replies with HTTP 1.1. If you support transfer encoding gzip, which most browsers do these days, you can gzip encode the entire page and set it all down. And unless the IDS knows how to decompress all that and decompress it in a way that you can't abuse it, eat all memory, and otherwise cause it to throw an error, you can bypass any signature in that.
Right, and the great part is if you're using gzip for the encoding, you can also in the gzip header, you can add two different fields that are arbitrary sized. They're just null terminated strings that in most gzip implementations, and if you're decompressing live, it just drops that data. It says, hey, this is a string, just ignore it. Well, so you can, if your gzip implementation, like a number of IDSs have right now, they don't support the name or the comment field, so you can append a bunch of extra junk, make them decode it, say, hey, this is an invalid decoding, and drop the packet then. And even worse, there's 3 different compression algorithms that the browser supports. There's gzip, deflate, and compress, which I can't remember if it's deflate or gzip, which are the same actual decompression, but one of them doesn't have the gzip header. And unfortunately, a number of IDS vendors are doing something wrong where they're actually writing signatures for the actual result of the gzip encoding. Unfortunately, there's enough, most of the compression algorithms support different levels of compression, so that adding if you're using the command line gzip interpreter, you use the gzip-9, compress it as much as possible. You can also do a gzip1, and the gzip signature will actually be very different.
Good examples in the Metasploit WMF module, we changed it so that it sent 1 byte at a time in different chunks, with each single byte being part of a total compressed body of a randomized WMF file. So the IDS vendors had to, think a little bit about how to decode this stuff, and unfortunately, they all picked the wrong approach to detecting it, which is to look for the static compressed data sent 1 chunk at a time, which is silly because as soon as you change the default options, it no longer works.
Well, one of the other great things you can do for all the different browser attacks that have been released lately, you can also encrypt them. Well, there's a number of ways. Everybody knows HTTPS exists. There's a number of ways you can do that as an evil person. One, you can purchase a certificate. I, for one, when I want to attack somebody, don't want to buy a certificate. Those track back to a person. Most of the certificate authorities out there that are require a photo ID, a passport, or a valid business license in order to get an SSL certificate. Well, I don't want to put my name attached to that out in the public. It's easier to track back to me. Well, the other thing you can do, you can compromise somebody else's box, put it up there, use their host for the exploits. Well, I'd rather not use some third party to do that. One of the great ways available nowadays, there's a bunch of people doing things to bypass the Great Firewall of China. They put up SSL-wrapped proxy servers that are CGI based. So you say, provide this other URL back through HTTPS. So you can proxy things like the examples that we gave in here. We proxied the Winamp attack. We say, hey, go grab my playlist from this web server. Proxy it back through and HTTPS, and your IDS has no idea what's going on there. Same thing. There are two currently publicly available HTTPS proxy servers that have valid certificates, so you're not going to get the pop-up saying, hey, do you want to accept the certificate? So if you embed that inside of an iframe, and then you do a CSS attack on some other site to embed that, then you can attack people. It'll be encrypted, so if they think they're being protected by an IDS, it'll be encrypted, and you go to a vulnerable website, say if MySpace had another cross-site scripting attack, you embed that, then you send exploits across the wire, and the IDSs are completely blind.
A little bit about attacking the IDS. So far what we've talked about is ways to evade the IDS in terms of application decoding, protocol decoding, IP fragmentation, things like that. Now we're going to say, okay, we want to attack this specific IDS. We want to find a way around this specific vendor's product, and there's different ways to do that. The easiest way, of course, is just flood the alert system. Find a way that you can actually launch an attack through the system, but make it so the alert that talks about that attack is either impossible to find or never triggers. There's also hardware limitations. Depending on how your IDS or IPS system is designed, you can do things to basically drain it of resources so that it can't possibly detect the attack that you're sending through it. Then there's things like session tracking. I mean, an IDS can only keep track of so many things at a time in memory, and as soon as you get over that level, you can then bypass attacks in that area. And finally, pattern matching and signature strength, where we actually start attacking the PCRE engines and the signatures and the kind of the string implementations used by different IDS vendors. So easy, attack the management system, attack the software. If you can flood the system with lots of attacks and you do a real attack through it, the user's going to have to go wade through 15,000 attacks to figure out which one is the real one. And sure, they know something bad happened, but trying to figure out what the real bad thing that happened is going to take them a really long time, and usually enough time for you to clean up, remove your tracks, and get out. There's a specific IDS out there that you can actually trigger over 1,000 events with a single packet. So just flood that packet about 15 times and then do your attack somewhere in the middle, and there's a really small chance someone's going to be able to detect what you're doing. And finally, just attack the user. Send the attacks in a way that it's really unlikely they're going to see the attack that you sent. You can do things like trigger a whole bunch of low-level alerts. They say, okay, well, I've got a whole bunch of really stupid false positives. You send a request that you know is going to trigger a low-level alert in the IDS, but is really valid. Like, say, uploading a JPEG image where the JPEG data is a whole bunch of NOP. So they keep sending all these NOP slide things being uploaded, and like, okay, well, this is an image some user's uploading. It's really not bad. And then when your real NOP slide hits, they don't notice that either. So things like that. Basically, if you know the IDS well enough, you can figure out how to trigger alerts in a way that the user really can't figure out what you did. They just know something bad happened.
It's really great for things like real-time consoles where they scroll IDS events. If you can force scrolling of IDS events, like the old ISS console, where you could force it to scroll IDS events, well, yeah, run Nix or send this packet. The one packet will generate 1,000 alerts per packet. You make it scroll so fast that the Windows will eventually crash.
Or run out of printer ink. What was that? That was a great alert. Did anyone see that screenshot of an ISS console that has this Windows printer management alert saying the printer has run out of paper? And as soon as it runs out of paper, the ISS engine no longer logs because it's waiting for the Windows API to finish that call. So anyways, it's a neat attack you can do where you actually attack the hardware. In this case, the poor little printer that just lost all its paper. Let's see, where am I with this? Okay, hardware limitations. How many people have heard someone saying, my IDS can do one